This video is going to show you how integrated rate laws are derived from differential rate laws. On the left you see the differential rate laws that we've been learning about, and on the right the integrated rate laws, which are just different mathematical forms of the same rate law. We have zero, first, and second order rate laws because those are the three most common rate laws that we see. We're going to start with a zero order reaction. And so for A going to products, the reaction is zero order in A when the concentration of A has no effect on the rate. And so the rate law you see is rate equals K times concentration of A to the 0 power, which means that A to the 0 power turns into a 1. So that reduces the expression to rate equals K. So here we have our differential rate law. Rate equals K. And rate we're going to rewrite as rate of reaction is negative delta A over delta T. Right? Remember that was what we learned in our related rates expression. So the next thing I'm going to rewrite is this delta A over delta T. In calculus we use, instead of using delta, which means change, we use lowercase d to mean sort of the same thing. So we're going to rewrite that as negative dA over dt equals K. And next, when we integrate, we're going to first rearrange this equation to move dt to the other side. We're going to move the negative sign to the other side. And then we're going to integrate each side of that expression. And that's what that little weird, funky S-looking thing is, taking the integral. When you take the integral of both sides from A sub 0 up to A at time t, and from time 0 up to time t on the right-hand side, then you end up getting this expression where A sub t, A at time t minus A at time 0, equals negative kt. And we're going to reorganize that into just a different mathematical form. A at time t equals negative kt plus A sub 0. And this is our final integrated rate law. And in the lower right hand corner I'm going to box that in with a nice gray box here. So this is our graph of the integrated rate law. You can see that the concentration of A, if we plot that along y as a function of time along x, then you get a straight line with a slope of negative k, and the y-intercept is A sub 0, the initial concentration of reactant A. We're going to move on to first order reactions. For a first order reaction, the differential rate law is rate equals K times A to the first power, and that's why it's first order, because it's A to the first power. So here we have our first order reaction written in a differential form. Now again, we're going to rewrite rate as negative delta A over delta T, and then we're going to rewrite that as negative dA over dt equals K times A. And we're going to rearrange a little bit. Move dt to the other side, and then we're going to take the integral of both sides, just like we did before. The integral of 1 over A turns out to be the natural log of A. That's just something you would have learned in calculus class. So you see that at the bottom now we have natural log of A at time t, and we subtract from that natural log of A at time 0, and that's because it goes from time t, and we integrate that down to the initial variable time 0. And then if we rearrange this equation just a little bit, then we move that natural log of A sub 0 to the other side, and we end up getting this final expression here, which is our integrated rate law for first order rate laws. Now we've looked at first order rate laws, and you can see the equation for the first order rate law in the upper right hand corner. Natural log of A equals negative kt plus the natural log of A sub 0. The graph below it in part B shows that the plot of natural log of A along y as a function of time along x should be a straight line. The slope is negative k, as you can see both in the graph and also in the equation above. And the y-intercept is the natural log of A sub 0, which is the natural log of the initial concentration of reactant A. So if you plot natural log of A as a function of time and you get a straight line, then that implies that the reaction is first order in that reactant. The graph shown in part A on the left-hand side is if you thought it might be zero order, you would have plotted concentration of A as a function of time, and you would see that the graph is not straight. The line is not straight. It exhibits what's known as an exponential decay, where the decline is rapid at first and then levels off. And we're going to talk about second order reactions. We're going to show this derivation. In a second order reaction, the rate varies as a function of lowercase k and as a function of concentration of A to the second power. That's why it's a second order reaction, is because it varies as the second power of the concentration of A. Here we have our second order rate law. The differential form of the rate law is written up here. And then we rewrite that where rate is again negative dA over dt equals k times concentration of A squared. We rearrange the equation again the way we did before. We move dt to the other side. We move the A variables to the left-hand side, and then we integrate. So you keep all the A's together and all the T's together. You integrate from time t to 0. And the integral of 1 over the concentration of A squared is going to end up being 1 over the concentration of A. And then there's a negative sign in there because it's to the negative 1 power. So that changes the signs here in case you were wondering how that negative went away. There was a negative here, but because this is A to the minus 2 power, when you integrate that, you get A to the minus 1 power, which is down here. But then you also end up with that minus 1 function that you have to deal with, which changes this sign, right? You multiply that by a negative 1, and that goes away, becomes positive. And then now we end up with this rearranged form of the second order integrated rate law. Now we have our second order integrated rate law in the upper right hand corner. 1 over concentration of A equals KT plus 1 over the initial concentration of A. The graph below it is if you plotted 1 over the concentration of A, and you can see in this graph it's a specific reactant, nitrogen dioxide. When 1 over that concentration is plotted as a function of time, you get a straight line. The slope of that line is equal to the rate constant K, and the y-intercept would be equal to 1 over the initial concentration of A, or in this case the initial concentration of NO2. The graph on the left is meant to show you that if you thought this reaction had been first order in NO2, then you would have plotted natural log of NO2 concentration as a function of time. And you would see that this graph is not linear. It is almost linear, but not quite. And so this would not give you nearly as straight a line as the one on the right. And these kinds of results would imply that this reaction is second order in NO2. So on the left we see another decay where it initially drops off more rapidly and then it levels off just a little bit. So to summarize, the left-hand side of the differential rate laws, the rate as they vary as a function of concentration of reactant. And then on the right are the integrated forms of the same rate laws, which just describe how the concentration of A changes with time. We know it's going to decrease over time because it's a reactant, but it describes how it decreases over time. What is the mathematical function that describes how the concentration changes over time?